Welcome to the video lecture series on digital image processing. For our last few classes, we are discussing on mathematical morphology and the application of mathematical morphology in digital image processing. So, in our last class, we have discussed about the application of mathematical morphology in image processing techniques, and we have talked about the morphological technique for boundary extraction. We have talked about the morphological technique for region filling. We have also discussed about the extraction of connected components using morphological operations. We have talked about what is a convex hull and how to detect or how to form the convex hull for a given point set using the morphological operations. Then we started our discussion on the thinning operation, thinning using the morphological operations, which we will continue today, and we will also discuss about the thickening operations along with some more applications. So, in today's lecture, we will complete our discussion on thinning using the morphological operations. We will discuss about thickening, and we will see that thickening is nothing but a dual of thinning operation. We will also discuss about the morphological techniques to obtain the skeleton of a given shape, and we have said earlier that the skeleton of a given shape is very useful for describing an object shape, and this description can be used for high level image understanding operations for image interpretation purpose. Then we will extend so far what till skeletonization whatever we will discuss, that is on the binary images, the application of morphological techniques on binary images. Then we will see that how to extend these morphological operations in gray level images. So, we will call it as gray level morphology, and we will see few of the operations, morphological operations like dilation and erosion, which is nothing but an extension of the binary morphology to gray level morphology, and a particular application like top hat transform that we are going to discuss in today's lecture. So, to start with, as we were discussing about the thinning, which we could not complete in our last lecture. So, let us just quickly review what we have done in our last class. So, for thinning, suppose we are given a point set say A, and this point set A has to be thinned by the structuring element B. So, a thinning operation using the morphological transformations can be obtained like this: A thinned with B, the structuring element B is defined as A minus A hit or mistransform with B. And we know that from set operations, this set difference operation can be implemented using set intersection and set complementation. So, this is equivalent to, the same definition is equivalent to A intersection with A hit or mistransform of B and complement of this. And we have said in our last class that for thinning operation, instead of using a single structuring element, what we use is a set of structuring elements, and the thinning is performed with the help of that set of structuring elements. So, in our case, for the thinning operation, we will have a set of structuring elements say B, and this set will contain a number of structuring elements. Let us call them as B1, B2, B3 and so on. Suppose there are n number of structuring elements. So, I will have up to Bn, where all these structuring elements in this set will follow a particular property that if I consider a structuring element say B I in this set, then this B I is nothing but a rotated version of set B I minus 1. So, if you rotate the set, the structuring element B 1, what I get is the structuring element B 2. Similarly, if I rotate the structuring element B 2, what I get is the structuring element B 3 and so on. So, every structuring element B I in this particular set of structuring elements is a rotated version of the previous structuring element, that is B I minus 1. Now, using this set of structuring elements, now the thinning operation has to be performed by applying each of the structuring elements in sequence. So, the thinning of the point set A now is to be implemented in this form. So, thinning of the structuring element with thinning of the point set A with the set of structuring elements B has to be performed in this way. So, first A has to be thinned with the structuring element B 1, this has to be thinned with structuring element B 2, and we have to continue like this. Then finally, we have to thin with the structuring element B n. So, look the operation that we are performing. We are taking the original set, original point set A, take the structuring element B 1 from the set of structuring elements B, thin A with B 1. Whatever thinned output you get, you thin that output with the structuring element B 2, thin this output with the structuring element B 3 and so on, and you continue until you thin all the intermediate results with the last structuring element, that is B n. And in this case, each of these thinning operations, that is when we say A is thinned with structuring element B 1, this follows this particular definition, that is A minus A hit or miss transform with the structuring element B 1. Now, this entire operation forms one pass of an iterative algorithm. So, the way we have to implement is that this entire operation, that is the thinning starting with the structuring element B 1 to the structuring element B n, this entire operation has to be done repetitively, say a number of times, until and unless we find that in two subsequent operations the output does not change. So, that is the stage when we get the when the algorithm converges and the output at that particular instant of time, at that particular time when the algorithm converges, gives the thinned version of the point set A with respect to the structuring element or set of structuring elements B. Now, let us take a particular example. Say here, as we said that the structuring element in this case is a set of structuring elements. So, in this particular example, we take say 8 structuring elements starting from B 1. So, this is structuring element B 1, structuring element B 2, structuring element B 3, structuring element B 4, structuring element B 5, B 6, B 7 and B 8. So, we consider 8 different structuring elements. Now, the structuring elements are something like this. So, the first structuring element B 1 consists of these points, and here we represent by cross. So, these are the points which are do not care points. So, when we try to find out the hit or miss transform of the point set A, with structuring element B1, what we will look for is that a translated version of this structuring element B1, at that translated location I should get a match at all these different point locations wherever the points are 1, and all these 3 points, the corresponding locations in the point set should also be equal to 0 or the background pixels. And we do not care about the condition of these 2 locations where we have put a cross. So, this is the first structuring element B1 in our set of structuring elements. The next structuring element B2, as we said, that if we rotate B1, what we get is B2. So, the structuring element B2 will be like this. This is our structuring element B2, and these are the do not care locations. We do not care about the corresponding locations in our point set A. Similarly, the structuring element B3 will be like this. These two are the do not care locations. Structuring element B4 will be like this, with these two locations as do not care locations. Structuring element B5 will be like this, where these two locations will be do not care locations. Structuring element B6 is this, these two being the do not care locations. Structuring element B7 is this, where these two are the do not care locations. And finally, the structuring element B8 will take this form with these two locations as the do not care locations. And for each of these structuring elements, we consider the origin of the structuring element to be the center location. That is, in each of these cases, the origin of the structuring element is the center location. These are the origins of different structuring elements, and so on. Now, let us consider a typical image, and if we try to thin that particular image with this set of structuring elements, what kind of thinned output that we are going to have. So, I take an image like this. So, I consider this particular binary image, which is to be thinned with this set of structuring elements. Obviously, in this case, this binary image is our given set A. Now, the way we have defined the thinning operation is that first we try to thin this point set A with the structuring element B1. Whatever output we get, that we thin with the structuring element B2. That output has to be thinned with structuring element B1. So, like this we will continue up to the structuring element B8, and this completes one pass. the entire operation has to be done second time, it has to be done third times, it has to be done fourth times and so on, until and unless we get a convergence, that is we get a situation that no other change, no change in the thinned output is possible. So, let us see, first let us consider the structuring element B 1 and try to thin this point set A with the structuring element B 1. Now, if you look here, you find that the points at which this particular structuring element B 1 will give a positive result for Misch and heat and Misch transform are these particular locations. So, this is one location, 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 this is one location and this is another location. So, only at these locations this particular structuring element B 1 are going to give positive results. The structuring element B 1 will not give positive results or a match anywhere else within this particular image. So, what we will do is, because our thinning operation is defined as A minus A heat or Misch transform with B. So, you find that if I remove these points from my original point set A, then after performing the thinning operation with the set B 1, this is the intermediate result that I get. Now, if I try to thin this with the structuring element B 2, you find that B 2 does not fit anywhere within this particular set. Try to thin with structuring element B 3 and you find that B 3 with the structuring element B 3, the points that we can remove are only these points. So, this is one point, this is one point and this is the other point. So, these are the 3 points which can be where this structuring element B 3 gives a match. So, what we do is we remove these points from the original point set A. So, at the end of the operation, this is what is going to be our thinned output, intermediate thinned output. Then you try to do the heat or Misch transform with B 4, you find that heat or Misch transform with B 4 in this particular image cannot remove any of the points present within this particular image. Try with B 5, again with B 5 the points that can be removed are these points. So, if I do this heat or Misch transform with B 5, I can remove this particular point, I can remove this particular point, similarly I can remove this particular point, I can also remove this particular point. So, these are the points which can be removed after heat or Misch transform, after performing the thinning operation with our structuring element B 5. So, if I continue like this, you will find that at the end the points which will remain within this image are these points. Okay. So, these are the points which will be remaining at remaining when the algorithm converges. Now, on this, if I impose the restriction that the connected component, that this thinned output that I get, that has to be M connected, in that case some more points are to be removed from this particular thinned output. So, to make it M connected, I have to remove this point, I also have to remove this point, I also have to remove this particular point, I also have to remove this point, I also have to remove this point, and this point also. So, at the end, this particular output that I get, the point set that I get, this is the thinned version of my input original point set A, which is thinned with the structuring elements or set of structuring elements B. And you find that because this is a skeleton kind of structure, it can be used for obtaining the description of a shape, which is useful for high level image understanding operation. Now, as we said that the thickening is a dual operation of thinning. So, just as in case of thinning, the thickening can also be represented, can also be defined in this form. So, thickening, which is represented like this with the structuring element B, this is defined as A union with A heat or mist transform with B. And in the same manner, here also B is a set of structuring elements, and because B is a set of structuring elements, if I consider the similar type of operation, then this thickening operation can be implemented in the same manner. So, first what I have to do is, so now this B is a set of structuring elements. First I have to do the thickening operation of A with the structuring element B 1. This has to be thickened with this has to be thickened with structuring element B 2, and we can continue this way. Finally, thickening with structuring element B n, and this completes our thickening operation. So, one way, because thickening is a dual of thinning, one way of implementing thickening operation is that for the given set A, you first compute the A complement. Then what you can do is, you just do the thinning operation of A complement with the set of structuring elements. After performing this thinning operation, if you take the complement of the thinned A complement, what we get is the thickening version of the given point set A. So, given a point set A, the first operation that you have to perform is you take A complement. Then what you do is, I make a set, say C, which is nothing but A complement thinned with the set of structuring elements B. And finally, if I take the complement of this set C, then what I get is the thickening version of this set A with the set of structuring elements B, which is nothing but the complement of the point set C. So, you find that this thickening operation can be implemented by thinning A complement. Now, there may be one problem, that while doing this operation, there may be some spurious points which will arrive in the thickened version of the point set A, which can be removed by some post processing operation like opening, closing and so on, and finally, what we get is the thickened version of the point set A. So, as we have done thinning, we have said that this thinning operations gives us some sort of skeleton of a two-dimensional shape. Now, there are morphological operations, the morphological technique, which can also be used to find out the skeleton of a given shape. Now, let us see how we can implement the skeleton of a given point set A by using the morphological operations. So, given a point set A, so now what we are discussing about the skeletonization. So, given a point set A, we can find out the skeleton of A, which let us represent as S of A. This can be obtained by this operation S K A, take the union for k equal to 0 to say capital M, where this SKA is defined as a dilation with k times dilation with B, the structuring element B, this minus again a dilation k times dilation with B and opening of this with set B. So, what this operation gives is, this particular operation gives us a number of subskeletons, and the union of subskeletons gives us the skeleton of the final of the given set A, which we represent by S of A. Now, this capital M in this particular case indicates that the last iterative step, as you find that here what we are doing is, when I do this A dilation with K B. So, this indicates that A is dilated with the structuring element B for successive k number of times, and this capital M indicates the last iterative step before A erodes to an empty set. So, we can define M as, M is nothing but maximum of k such that A eroded with K B, this is not equal to a null set. So, this M indicates the maximum number of iteration before our given set A erodes to a null set. Now, as we have found that the skeleton of a given set A, given point set A with respect to structuring element B can be found out by repeated application, by successive application of erosion with respect to the given structuring element B and an opening operation with the same structuring element B. Similarly, given the skeleton, we can also reconstruct our original point set A. So, this can be done in this fashion. So, given a point set A or the skeleton A, when we have all the subskeletons say SKA, what we can do is, we can erode this SKA with the structuring element successively k number of times, where SKA is a subskeleton, and take the union of this for k equal to 0 to capital M, and this is what is our original point set A. So, let us illustrate this skeletonization and finally getting back our original point set A from the subskeletons with the help of an example. So, the example is like this. For this skeletonization, the structuring element B we will consider is a 3 by 3 structuring element like this. So, this is our structuring element which we can use for skeletonization purpose, and in this case the origin of the structuring element is the center element. And now, let us take an image like this. So, this is the given image. Now, what we do is, on this side let us put the iteration number k. So, on this side we will put the iteration number k. So, this is k equal to 0, k is equal to 1 and k is equal to 2. And on this side let us put the successive skeletonization operation. So, I put A erosion with K times B. This column, let us, it represents A erosion with K times B, then opening with B. This column, suppose it represents SKA, that is the subskeleton. This column, let us, it represents the skeleton SKA, where we take the union of the subskeletons SKA, where K varies from 0 to capital M. This column, let us assume that it represents SKA dilated with KB, and we will see what does this column represent is the union of this term. So, if I do it like this, if I erode this given point set A with respect to our 3 by 3 structuring element, then after eroding it for the first time, the kind of output that I get is like this. So, this is the output that I will get after eroding this given point set A with our 3 by 3 structuring element once. And if I erode it for the second time, then the output that we will get is this. On this column, where if I perform the opening operation of this successively eroded images, then what I get over here is like this. In this particular case, what I will get is this, and here this will be a null set. I will not get any point in this particular case, that is after eroding for 2 subsequent operations, eroding it twice and then doing the opening with this structuring element B. Now, from here what I get is, I get the intermediate or subskeletons, as we have defined the subskeleton as a difference operation, the difference of A eroded by A eroded with K times B minus A eroded K times B opened with B. So, if I take the difference of the first column and the second column, then what I get is our subskeletons. So, in this case the subskeleton will be like this. So, you find that this is nothing but the difference of the element in the first column and the element in the second column. Similarly, in the second case, the subskeleton will be like this, and in the third case the subskeleton will be like this. Now, if you take the union of all these subskeletons, as we have defined that the final skeleton is the union of all the subskeletons. So, the final skeleton will have this particular shape. So, this is our here we will get it like this. So, find that this is the element which is actually our skeleton SA. And here you find that when I get this skeleton is not really connected. So, what we get is a disconnected point set, and that is not unnatural, because when we have performed the morphological operations, nowhere we have guaranteed the connectivity. So, it is quite possible that given a set, if I try to find out the skeleton of that point set by using morphological operations, then it may lead to a skeleton which is unconnected. Now, let us say that given these subskeletons, whether it is possible to find out the original set A by using the reverse process, that is, while doing the skeletons, what we have used is the successive erosion. Now, in the reverse process, what we have used is the successive dilation. So, after defining those dilation operations as we have defined earlier, now we can try to reconstruct the original point set A from these subskeletons. So, here you find that in the fifth column, which is nothing but SKA, that is subskeleton A, eroded successively k times with the structuring element B. So, if I do this, in that case this particular column will give me this output. And finally, the last column, which is nothing but union of all these operations. So, if I take the union of all of them, what I get is this. So, this is what I get. So, if I compare now this output with our original point set A, you find that this is nothing but the point set A which was given. So, by this type of morphological operations, it is possible to obtain the skeleton of a given shape, and once I have these subskeletons while doing this skeletonization operation, then from these subskeletons it is also possible to obtain the original point set A by applying the inverse operation. So, so far what we have discussed, all the morphological operations that we have discussed, they are meant for the binary images. Now, let us see whether we can extend these binary morphology, these morphological operations to gray level images as well. Obviously, our assumption will be that as we have started, that every image we should be able to represent as a point set if we want to apply the morphological operations on the image. So, here also the gray level image we should be able to represent as a point set or set of points. So, let us assume that we are given a point set A in say n dimensional Euclidean space. So, this A represents a point set A in n dimensional Euclidean space. Now, out of for this point set A, the first n minus 1 components, the first n minus 1 coordinates, this represents a spatial domain. and the nth coordinate this represents the value of the function. So, this is our basic interpretation. So, what we are doing is we are taking a set A, a point set A in n dimensional Euclidean space. So, if I take a point belonging to that set A, then first n minus 1 coordinates of that particular point, this represents its location in the spatial domain, and the nth coordinate, that is the last coordinate, this represents what is the value of the function at that particular location in space. So, for example, if I take a 3-dimensional point, say 5, 3, 7, or in general, if I assume a coordinate system, say x, y, z. Now, what does it mean? This means that I have a 2-dimensional space which is given by x, y, and z is the value at that location. So, I can represent this as z is equal to some function f x y. So, you find that this first two coordinates x and y, this represents a spatial domain, and the last coordinate, that is the third coordinate, this represents what is the value at that particular location. So, similarly, for a Gray level image will represent as a triplet like this, say 5, 3, 7, where this 5, 3, this represents a location in a 2-dimensional space, and the last component 7 represents what is the value in that particular location. So, when I have a Gray level image, this value represents what is the intensity value or the Gray level value at location 5, 3 in the image. Now, find that if I have this sort of interpretation of a Gray level image, I get some advantage. Now, what is the advantage? The advantage is that now the Gray level image typically represents a topological sketch, and the intensity value I can assume that it represents the height within that topological sketch. So, given this, when I have this sort of interpretation, now to extend our Gray level, extend our morphological operations to Gray level images, we try to define two different terms. One of the term we will define is the top surface, and the second term that we will define is what is called umbra. Now, what is this top surface? We have said that we are assuming a point set A which is in n dimensional space, n dimensional Euclidean space, and we have said that the first n minus first components that represents spatial domain, and the last component, that is the nth component, represents a value of the function at a point in the in space. Okay. Now, over here, if I take like this, that suppose I have, if we consider in 2 dimension, suppose I have a set of points something like this, say 1, 1, 1, 2, 1, 5, then say 2, 3, then suppose 2, 7, then say 3, 1, 3, 3, and say 3, 5. Suppose these are the set of points which are given. Okay. Now, if you analyze this point set, I find that for these points, the first component is same, which is equal to 1. For these points, the first component is again same, which is equal to 2, and for these points the first component is again same, which is equal to 3. So, as we have said that the first component represents a point in space. So, coming to our n dimensional space, the first n minus first components represents the space. So, what we do is, for each n minus 1, we try to find out what is the maximum value of the nth component in set A. As in this case, for all these components, the maximum value is 5. For this case, the maximum value is 7, whereas for this case, the maximum value is again 5. So, the top surface consists of these values 5, 7 and 5. So, the top surface consists of the points 1, 5, 2, 7 and 3, 5. So, these are the points which makes the top surface. So, coming to our formal definition, what I have is, for each of n minus for each n minus 1, I try to find out what is the maximum value of the nth component in set S in the given set A, and that maximum value forms the top surface. So, formally we can define the top surface as like this, that given a set A, the top surface T A at location x, where x is our n minus 1 dimensional tuple. This will be given by maximum of y, where x y belongs to set A. So, you find that this x y is an n dimensional, an n tuple, x is n minus 1 tuple, and we try to find out the maximum y for each n minus 1 tuple, which is the top surface. And for these cases, we also define the region of support, which we define as f. This region of support is defined like this. It is x belonging to n minus 1 dimensional space for some y belonging to 1 dimensional Euclidean space, such that x y belongs to set A. So, you find that we have the region of support, we have the top surface T A, and diagram it with the help of a diagram. We can represent it like this. Suppose we have a set of points given like this. So, suppose this is our x dimension, this is y dimension, this is z dimension. So, the projection of these points on the x y dimension, this gives us the region of support F. Okay. And if I take the maximum of the values, maximum of z values at each point in F, this is what gives us the top surface. Say T of A. Now, we define the umbra. So, given a region of support, say F, which is a subset of n minus 1 dimensional Euclidean space. So, one more thing here, you find that this top surface, it is something like a mapping function. We can represent this as a mapping function which maps this region of support F to a 1 dimensional Euclidean space. Now, given this top surface, which as we have said that it is a mapping function, we can define umbra of F as UF, which is obviously a subset of an n dimensional Euclidean space. So, F is an n minus 1 dimensional Euclidean space. If I take the Cartesian product with 1 dimensional Euclidean space, what I get is n dimensional Euclidean space. So, now this UF, the umbra of the top surface, this is defined as the set xy belonging to obviously F Cartesian product with 1 dimensional Euclidean space epsilon, where this y is less than or equal to f x. So, what does it mean? This expression means that umbra consists of all the points including the top surface, all the points below the top surface including the top surface itself. So, the top surface gives you the maximum value at a particular location in the region of support in the spatial domain, and umbra is everything below the top surface including the top surface. So, after giving these definitions, let us see that how the dilation and erosion operation can be defined in case of gray level images. So, as we have said that a gray level image is a subset of a 3-dimensional space. So, given a gray level image, so we define it like this. So, suppose we have given two regions of support, one is F and other one is K. These region of supports are obviously in dimension n minus 1 dimensional Euclidean space. In case of gray level image, this will be a 2-dimensional Euclidean space. We have two top surfaces F, which maps the region of supports into 1-dimensional Euclidean space, and K, which maps the region of support K again to 1-dimensional Euclidean space. Then we can define the dilation of F and K as the top surface of the dilation of umbra of F with the umbra of K. So, what we have to do is, given a gray level image, we have to find out the umbra of it. Similarly, given a structuring element, we have to find out the umbra of the structuring element. Then we have to dilate the umbra of the image with the umbra of the structuring element. Then we have to find out the top surface of this dilated output. So, you take the umbra of the gray level image, you take the umbra of the structuring element, dilate these two umbras, then the top surface of this dilation tells you what is the dilation of the given gray level image with respect to a given structuring element. And in the same manner, the erosion of in case of gray level image, this can also be defined in terms of the top surface of erosion of umbra of F with the umbra of K. So, you find that extension of the morphological operations from binary image to gray level images are quite simple. What we do is, we convert the images into their umbras. Similarly, we convert the structuring element into its umbra, then take the erosion or dilation of the corresponding umbras, and the top surface of this erosion or dilation gives the corresponding erosion or dilation of the gray level image with respect to the corresponding with respect to the given structuring element. So, with this we stop our discussion on erosion and dilation operations, discussion on morphological operations. So, in this discussion what we have done is, First, we have defined the basic morphological operations like erosion and dilation, and we have seen that these basic morphological operations are implemented by different set operations. Our basic assumption is any form of image on which these morphological operations are to be applied, they are to be represented as point sets, and then all subsequent applications of these morphological operations in case of image, whether it is for a binary image or for a gray label image, we have seen that they are nothing but applying the basic erosion and dilation operations along with few set operations in different order. And the net result of applying these morphological operations is that given any point set or given an image, we can regularize an object present in the image. By regularization, what I mean is, in the object region, if there are some noises, we can remove those noises by morphological operations. In background region, if there are some noises, we can remove those noises by morphological operations. If two object regions are connected to each other because of some noise, we can remove that. So, these are various regularization operations that we can perform through morphological operations. The basic aim is, of course, mathematical morphology is very wide, but we are concentrating on a very narrow application of it in our image processing applications. And the basic purpose of doing this regularization is we can have a better description of object regions or the different foreground regions. Now, let us see some questions on today's lectures. So, the first question is, does morphological skeletonization guarantees connected skeleton? Second question, what is top surface? The third question, what is umbra? The fourth question, define grayscale dilation and erosion operations. The fifth, if an image contains light objects against varying background, what kind of operation do you suggest to detect the object region? Thank you.